Human vision is amazingly beautiful and complex. It all started billions of years ago, where small organisms developed a mutation that made them sensitive to light. Fast forward to today, and there's an abundance of life on the planet which all have very similar visual systems. They include eyes for capturing light, receptors in the brain for accessing it, and a visual cortex for processing it. Genetically engineered and balanced pieces of a system which help us do things as simple as appreciating a sunrise. But this is really just the beginning. In the past 30 years, we've made even more strides to extending this amazing visual ability not just to ourselves, but to machines as well. The first type of photographic camera was invented around 1816, where a small box held a piece of paper coated with silver chloride. When the shutter was open, the silver chloride would darken where it was exposed to light. Now, 200 years later, we have much more advanced versions of the system that can capture photos right into digital form. So we've been able to closely mimic how the human eye can capture light and color. But it's turning out that was the easy part. Understanding what's in the photo is much more difficult. Consider this picture. My human brain can look at it and immediately know that it's a flower. Our brains are cheating since we've got a couple million years worth of evolutionary context to help immediately understand what this is. But a computer doesn't have that same advantage. To an algorithm, the image looks like this. Just a massive array of integer values, which represent intensities across the color spectrum. There's no context here, just a massive pile of data. It turns out that the context is the crux of getting algorithms to understand image content in the same way that the human brain does. And to make this work, we use an algorithm very similar to how the human brain operates, using machine learning. Machine learning allows us to effectively train the context for a dataset, so that an algorithm can understand what all those numbers in a specific organization actually represent. And what if we have images that are difficult for a human to classify? Can machine learning achieve better accuracy? For example, let's take a look at these images of sheepdogs and mops, where it's pretty hard even for us to differentiate between the two. With the machine learning model, we can take a bunch of images of sheepdogs and mops, and as long as we feed it enough data, it will eventually be able to properly tell the difference between the two. Computer vision is taking on increasingly complex challenges and is seeing accuracy that rivals humans performing the same image recognition task. But like humans, these models aren't perfect. They do sometimes make mistakes. The specific type of neural network that accomplishes this is called a convolutional neural network, or CNN. CNNs work by breaking an image down into smaller groups of pixels called a filter. Each filter is a matrix of pixels, and the network does a series of calculations on these pixels, comparing them against pixels in the specific patterns the network is looking for. In the first layer of a CNN, it is able to detect high-level patterns like rough edges and curves. As the network performs more convolutions, it can begin to identify specific objects like faces and animals. How does a CNN know what to look for, and if its prediction is accurate? This is done through a large amount of labeled training data. When the CNN starts, all of the filter values are randomized. As a result, its initial predictions make little sense. Each time the CNN makes a prediction against labeled data, it uses an error function to compare how close its prediction was to the image's actual label. Based on this error or loss function, the CNN updates its filter values and starts the process again. Ideally, each iteration performs with slightly more accuracy. What if instead of analyzing a single image, we want to analyze a video using machine learning? At its core, a video is just a series of image frames. To analyze a video, we can build on our CNN for image analysis. In still images, we can use CNNs to identify features. But when we move to video, things get more difficult, since the items we're identifying might change over time. Or, more likely, there's context between the video frames that's highly important to labeling. For example, if there's a picture of a half-full cardboard box, we might want to label it packing a box or unpacking a box, depending on the frames before and after it. This is where CNNs come up lacking. They can only take into account spatial features, the visual data in an image, but can't handle temporal or time features, how a frame is related to the one before it. To address this issue, we have to take the output of our CNN and feed it into another model which can handle the temporal nature of our videos. This type of model is called a recurrent neural network, or RNN. While a CNN treats groups of pixels independently, an RNN can retain information about what it's already processed and use that in its decision-making. RNNs can handle many types of input and output data. In this example of classifying videos, we'd train the RNN by passing it a sequence of frame descriptions, empty box, open box, closing box, and finally a label, packing. As the RNN processes each sequence, it uses a loss or error function to compare its predicted output with the correct label. Then it adjusts the weights and processes the sequence again until it achieves a higher accuracy. The challenge with these approaches to image and video models, however, is that the amount of data we need to truly mimic human vision is incredibly large. If we train our model to recognize this picture of a duck, as long as we're given this one picture with this lighting, color, angle, and shape, we can see that it's a duck. But if you change any of that, or even just rotate the duck, the algorithm might not understand what it is anymore. Now, this is the big picture problem. To get an algorithm to truly understand and recognize image content the way the human brain does, you need to feed it incredibly large amounts of data of millions of objects across thousands of angles, all annotated and properly defined. The problem is so big that if you're a small startup or a company lean on funding, there's just no resources available for you to do that. This is why technologies like Google Cloud Vision and Video can help. Google digests and filters millions of images and videos to train these APIs. We've trained a network to extract all kinds of data from images and video so that your application doesn't have to. With just one REST API request, we're able to access a powerful pre-trained model that gives us all sorts of metadata. Here's how easy it is to call the Cloud Vision API with curl. I'll send this image to the API, and here's the response we get back. Billions of years since the evolution of our sense of sight, we found that computers are on their way to matching human vision, and it's all available as an API. If you'd like to know more about the Cloud Vision and Video APIs, check out their product pages at the links here to see how you can easily add machine learning to your application. Thanks for watching.